Hello and welcome to the Ukrainian Maths and to the third video of the series on logarithms, where we learn how to solve these logarithmic expressions and equations knowing just one simple logarithmic formula. First of all, where do we get this fundamentally important formula from? And it appears that it is so linked to the logarithm that we derive it from the definition itself. So as a reminder, and go check out my first video, the logarithm is defined as the value of the logarithm is exactly the value that we need to get the result b, the number b here, by exponentiation when we raise the base number a to the value of c. So if log to the base a of b is equal to c, then a raised to the power of c must be equal to b. So if, for example, we have log to base 2 of 8 equals to 3, then I have to have that 2 raised to some power, which is a logarithm, must be equal to the result 8. And therefore, my logarithm is equal to 3, because 2 raised to the third is equal to 8. And now, we are going to use this definition in order to get the formula. So we begin by the logarithm identity, and we will again rewrite this as a raised to the power of c is equal to b. But since we know that this thing here is the identity, it does not matter if I use the right hand side or the left hand side of this identity. So instead of the c here, I will plug in the left hand side, and therefore obtaining a raised to the power of the left hand side log to a of b, and this all is even now equal to b because we do not change the right hand side. So in the end we have a raised to the log to a of b equals to b. As you can see here, we have cancelled out the exponentiation and the logarithm action, so this formula is called the log cancellation formula, or also the fundamental log identity. So fundamental log identity. So all this formula is saying is, if I have some exponentiation with the same base here in the power and in the logarithm, then by combining the base number with the exponent of the logarithm, I can cancel out the exponentiation process and just get b. So now that we have this formula, we are now ready to solve the equation. So how do I apply this thing to this equation right here? Because before, as you can see below, I used to have some exponentiation, and here I just have some identity with logarithm and no powers. So to make this easier to find this exponentiation, we are allowed to do some simple trick. We are allowed the exponent to the left hand side and the right hand side to the same base. And here I'm going to take the base 2 because I already have the base 2. So we'll rewrite this equation as 2 raised to the power of the left hand side, so it's log 2 of x minus 3, and on the right hand side I also have the base 2 raised to the power of the right hand side, so it's log 2 of 5 minus x. With powers and with exponents, we are always allowed to do this operation. We're always allowed to exponent the left hand side, the whole left hand side, and the whole right hand side. The reason for that is going to be explained in this special video dedicated to exponents. Okay, so now we've achieved what we wanted. So we now have same basis in the exponent and in the power, meaning that we can just cancel things out and obtain the results we have in the argument of the logarithmic function. So on the left hand side, I'm going to end up with x minus 3, and on the right hand side, I have 5 minus x. So here, this thing here is just a simple linear equation. So I can move x to the left, minus 3 to the right, and get 2x is equal to 8, divide by 2 and get x is equal to 4. However, the careful viewers could have spotted that I forgot to do one important thing. If you watched the last video, then you know that the logarithmic function has certain restriction. I am not allowed to consider logarithmic function of any number. If I have the argument, then the argument of logarithmic function has to be strictly positive, meaning that I have to consider certain restrictions. And they, this time, are that the both arguments are positive, so x minus 3 is positive, and simultaneously 5 minus x is also positive, meaning that we end up with the restrictions or with the system of linear inequalities, and this results in x greater than 3 and x less than 5. To solve this one, we can look at the number line of x. So we have our 3 on the left, 5 on the right, and we know that our x has to be on the right of 3, and since it's less than 5, it has to be on the left of 5. So it has to be in both regions simultaneously, meaning we must take the intersection of the two half lines, and this delivers the final restriction of our x being the interval from 3 to 5, excluding the ends of the intervals. So we have to check if our possible solution belongs to this interval, and in fact 4 lies inside of this interval. So we know that 4 belongs to the restriction, and therefore we can now say that the answer is in fact the root x equals to 4. So let's look at the first example, at the very similar example, to do just the same thing and see how this works again to memorize it better. So again, we have log to 8 of x minus 10 equals to log to 8 of 3 minus x. I will do the same trick with exponentiation in order to use our log cancellation formula, and we'll have 8 raised to the left hand side, so log to 8 of x minus 10, and on the right hand side I'm going to have a raised to the power of log to 8 of 3 minus x. So again, I can use my log cancellation formula because I have same basis, and I have some result of exponentiation which I can just write down here. So I have x minus 10 equals to 3 minus x, which is again a simple linear equation. So I move minus x to the left, getting 2x, and minus 10 to the right, getting 13. I divide by 2, and I obtain x equals to 6.5. So, okay, but what about the restriction? We haven't checked it yet at all. So let's do this one. Let us do restrictions. X minus 10 has to be strictly positive or greater than 0, and 3 minus x has to be positive as well. So we have the system of linear equations again, resulting in x greater than 10 and x less than 3. This here looks a little bit odd. So if we consider the number line of x, then we have our number 3 on the left and the number 10 on the right. So we know that our axes, our possible solutions, or possible numbers have to be simultaneously on the right of 10 and on the left of 3. So they have to be greater than 10 and less than 3 simultaneously. But this would mean that that would lie in the intersection of the regions. However, there is no intersection of the regions, so I even theoretically cannot have any solutions. So the restriction is no possible solutions. So I even theoretically cannot have a root, meaning that my answer does not belong to my restriction, which means that I have to say that my answer is no roots. So as we can see here, it is important to know how to solve logarithmic equations, but it is even more important to check my restriction first, because first of all it might appear that my root does not belong to the intersection or to my restrictions, or it can also happen that there is no restriction, or that the restriction says that I just cannot have any roots. So in the next examples, we are always going to begin with solving or finding restrictions. And we are going to do this just right here. So we have our restrictions, again, that the arguments of logarithmic functions have to be positive. So x plus 1 is strictly positive, and x minus 1 is also greater than 0, ending up with x greater than minus 1 and x greater than 1. So here we have, again, two inequalities, but this time to the same side. So we have our number line of x, we have our minus 1 on the left and plus 1 to the right. So which one is more restrictive? Which inequality delivers more information? So I know that by first inequality, I have to be on the left of minus 1, and by the second one, I have to be on the right of the minus 1 and on the right of plus 1, meaning that I have to be in the intersection of these two half lines or regions, ending up with an interval of plus 1 to plus infinity. So this is my final restriction. Now we are allowed to do our exponentiation trick. This time again, I'll have to take the base 2 because I need the same base of a power and of a logarithm. So I have 2 raised to the left hand side, and I have to take the whole left hand side. So I have log 2 of x plus 1 plus log 2 of x minus 1. The right hand side is the exponentiation again, so I have base 2 and the right hand side being 3. The right hand side is easy. We have 2 cubed, which is just an 8. However, the left hand side does not seem this friendly, because here I have some sum of logarithms, and in my log cancellation formula, I have only some power with the base and some logarithm at the top. So I somehow have to split these powers. And here, instead of using logarithmic formulas, which we haven't learned yet, we are going to use the well-known power formulas. So we know, and for those of you who don't know, go check out my powers video, we can split our sum using product. So here we are going to end up with 2 raised to the power of log to 2 of x plus 1 times 2 raised to the power of log to 2 of x minus 1. So we splitted these into the product of 2 powers, and here we can already use our log cancellations formulas because we have just the simplest appearance of the terms here. So it is going to be just x plus 1 times x minus 1 equals to 8. And this here is finally a simple quadratic equation which we'll solve by expanding the left hand side, obtaining x squared minus 1, and on the right hand side we still have an 8. So now we'll add up 1, having x squared plus equals to 9, and since this is a quadratic equation, we commonly have 2 roots, just as here we have a root x equals to plus 3 or x equals to minus 3, because both of these numbers square give me a 9. So we now check if both of these belong to the restriction, and it happens that only one does. So the plus 3 belongs to the interval of 1 plus infinity, and minus 3 does not. So our final answer is therefore x is equal to plus 3. So we write x is equal to plus 3. Moving forward to the next example, we have log to the base of 3 of x plus 1 plus log to the base of 3 of x plus 3 equals to 1. So this is just a similar example in order to memorize how to solve these things. Again, as before, we have restrictions, x plus 1 greater than 0, and x plus 3 is greater than 0 as well. So we have x greater than minus 1 and x greater than minus 3 simultaneously. Having a number line, we have that in both cases, the minus 3 and the minus 1, we have that in both cases, x has to be on the right. So the intersection delivers us x is in the interval of minus 1 to plus infinity, which is also logical because the more restrictive inequality is actually x greater than minus 1. So we end up with just an interval of from minus 1 to plus infinity. Again, we use our exponentiation trick, this time with the base of 3, because here we have the base 3, and therefore we have 3 raised to the power of log 3 of x plus 1 plus the whole left hand side log 3 of x plus 3 equals to 3 raised to the first power. So the right hand side is easy, we have just 3, the left hand side has to be split. We use the sum product formula for powers and we obtain 3 raised to the log to 3 of x plus 1 times 3 to the power of log to 3 of x plus 3. Just as before the log cancellation formula, the exponentiation cancels out, and we end up with x plus 1 times x plus 3, which thankfully is again just a simple quadratic equation. So we expand the left hand side using our product, and we end up with x squared plus 3x plus x and plus 3 equals to 3. From here we see that our 3 cancels out and we have x squared plus 4x equals to 0. Here we can take x out of the brackets, so we have x times x plus 4 equals to 0. So we know that when in real numbers we have that the product is equal to 0, then either of the factors has to be equal to 0. So we have only 2 possible solutions, just as usual. We have that either x is equal to 0 or x plus 4 is equal to 0, meaning that either x is equal to 0 or x is equal to minus 4. Checking off these solutions again, we have that this belongs to the restriction and this does not, meaning that the final answer is just a single root x equals to 0. Now we'll look at a similar example, but this time instead of the plus sign between logarithms, we are going to have the minus sign. Okay, so let's look at this one, and probably it'll be similar. Anyway, we begin with restrictions. So we have restriction that both have to be positive. So x minus 2 and x plus 1 are strictly positive, meaning that we have x is greater than 2 and x is greater than minus 1. Just as before, the x greater than 2 is more restrictive. So the final restriction is from 2 to plus infinity. And again, we have the same plan, exponentiation to the base of 3, because this time we have the base 3, so it's 3 raised to the log 3 of x minus 2 minus log 3 of x plus 1 equals to 3 to the first. Okay, the right hand side, usual, simple. The left hand side, however, this time we have the minus sign, so we cannot split this the way we did before. This time we are going to have a fraction, because when with powers we have the minus sign, then it is going to give us a fraction, which you can also see in this video above. So we have 3 raised to the log 3 of x minus 2 over the index we have here with a minus sign. So it's 3 raised to the power of log to 3 of x plus 1. So again, log cancellation formula, we have x minus 2 over x plus 1 equals to 3. Many of you who see this might think, well, but I am not allowed to divide by 0. So let's look, do we ever divide by 0? And actually we do not, because to have a 0 in the denominator, we have to have x is equal to -1. But this case was, thanks God, already excluded in the restriction we have here on the right. So we now can just multiply both sides by x plus 1, having x minus 2 equals to 3 times x plus 1. And again, this is just a simple linear equation, so x minus 2 equals to 3x plus 3. And by moving the terms around, we have that 2x, so we move x to the right and 3 to the left, is equal to -5 divided by 2, x is equal to -2.5. So we have to check if this solution belongs to our restriction, and it appears that even though we had a one possible solution, it does not belong to a restriction. So therefore the answer is we have no roots. However, if there's the only way to solve this equation, this division, it's okay if we have just two logarithms that are subtracted. However, what if I have multiple? If I have log minus log is equal to minus log plus log or something. Well, this then gets a little bit harder because I have to divide multiple things. And what if I had an inequality instead of an equality? And things are going to get complicated. And to make this one easier, we can use a trick. So we want to turn this minus sign to a plus sign. And to do that, we can simply move this term to the right hand side. So we'll have log 3 of x minus 2 is equal to 1 plus log 3 of x plus 1. So by doing what we did before, by exponentiating to the base of 3, we'll end up with 3 raised to the log 3 of x minus 2 is equal to 3 raised to the 1 plus log 3 of x plus 1. And this time, we do not longer have any minus signs, meaning that we can split these using our usual product rules. So we'll have x minus 2 by log cancellation formula on the left, and 3 to the first times 3 to the log 3 of x plus 1 on the right hand side, meaning that we just have x minus 2 equals to 3 times x plus 1, which is exactly the equation we had from above. So here we have x is equal to -2.5, which we already know does not belong to our restrictions. So with some combinations, some linear combinations, where we have logs with plus and minus signs, we actually have two ways to solve them. We can just exponentiate strictly from the beginning, or we can move the terms around a bit and make the thing a little bit easier. The last one I have for you is a little bit harder because some of you might say, well, all of those are easy, maybe your formula is not so good at all. And to show you that even with the harder ones you can still use the formula, we'll look at the example here where we have log to 2 of x plus log to 4 of x. So here we have different bases. So normally if we knew or remembered all these formulas, we'd have to say that log 4x is equal to log to the base of 2 squared of x. And here we can take those two out of equation and get 1/2 of log 2x. However, it might happen that first of all you forget the formula. Secondly, well, what if you didn't learn them, or what if just something happened? We're all people. So I want to show you the way to live by without it. So our plan is exactly what we had before. We first have to find restrictions, and in this case they are straightforward. Both of the arguments, so just x has to be positive. So this is our restriction. But when we choose the base to exponentiate, this time we have two choices. So you might ask, okay, so which one do I take? The the second base or the fourth base? And the answer is, well, maybe we don't know. So why don't we just try both and see what works best? So let's say I exponentiate to the base of 4. Then I have 4 raised to the left hand side. So log 2x plus log 4x is equal to 4 raised to the first power. The right hand side is easy as usual. We have 4, but the left hand side has to be splitted. So we have 4 raised to the power of log 2x times 4 raised to the power of log 4x. At least one bit of the left hand side is easy, because here I have the same base, which is why we took the base of 4, so that at least one of these splitted things work. So here we are going to have x equals to 4 times something here on the left. So now I have to figure out the way how to use my log cancellation formula. And usually for it to happen, I need to have same base in the power and in the logarithm. So I somehow have to rewrite my 4. And the easiest way to do this is again to recall that 4 and 2 are connected. 4 is 2 squared. So I'll write this one down here. I have 2 squared, all to the brackets, and raised to the power of log 2x. So I rewrote my 4 as 2 squared. And what we know about powers, and again, this is the idea of the whole thing. Instead of learning many logarithmic formulas, we try to use the ones that we already know. Here we know that when we have exponentiation, consecutive exponentiation, it really does not matter in what order I do it. I can first square it and then raise to this power, or I can first raise to the logarithm and then square. So here we'll change the order. We'll have 2 to the power of log 2 of x. The whole result of that must be squared, then multiplied by x, and this should be equal to 4. And the reason we did that is so that we finally end up with something where we can use our log cancellation formula. So here we finally have same basis and some result of x. So we can finally write x in the brackets squared times x is equal to 4, which is a relatively simple equation where we have x squared times x to the first, we get x third, because x raised to the second times x raised to the first is x raised to the 2 plus 1 equals to 4. And from here on, we can use our roots. So x should be equal to the third root of 4. For those unsure, go check the roots video, maybe on my channel, maybe on some other channel. So we know that to solve this equation, we take the third root, and we have this number here, which have to be checked on the sign. And we know that this number is in fact positive. So it is positive and therefore belongs to our restriction. So therefore, we have found a root, and answer x is equal to the third root of 4. Okay, so we said that the exponentiation to the base of 4 works. But what if we were to do the same, but with the base of 2? Would it also work? Would it be perhaps easier? Well, okay, let's look at this one. 2 raised to the left hand side log 2x plus log 4x is equal to 2 raised to the first power. So as before, the right hand side is easy, it's just 2. The left hand side has to be split, log 2x times 2 log 4x. So the first bit's easy, it's just x times 2 log 4x is equal to 2. And when we look at this thing, it is not this easy to get from 2 to the 4, because in order to use our formula, we want to have 4 instead of 2. And in fact, the easiest way to do this would be to write the root of 4 with the same idea that the root for the square root of 4 is 2, And secondly, we can change the order. We can first raise it to the power of the logarithm and then take the root from the whole result. However, if we look at this and compare it with the first idea, and we see that this here gets quite complicated. So from just trying this for 1 minute, we notice that, okay, this here doesn't work, so I'll take another base.